So I'm Gábor Horváth and I'm going to talk about lifetime related static analysis check. So first I will talk about why is it important to find such errors, and then I will do a whirlwind tour of the lifetime analysis as it was defined by Herb Sutter. Just out of curiosity, how many of you saw Herb Sutter's keynote on last year's CPPCon? Okay, don't worry, I will go through the main points and then I will highlight some implementation details that might be interesting for those who are interested in compiler technology, and then I will move on to show you the results, how successful this method is, and what are the plans to upstream it to the mainstream Clang compiler so everybody can use it. Okay, so Microsoft reported that about 70% of all the security patches they issue are memory errors. So this shows us it is very important to actually have some tools that help us catch those errors. And C++ has many possible sources of such errors. For example, the manual memory management and the temporary objects, pointer-like objects. So it is not easy to deal with all of those problems in this language. Fortunately, we have some tools. For example, we have the Clank, the sanitizers, but these dynamic analysis tools are only good for certain architectures. For example, if you are developing for an embedded platform which does not support virtual memory, then you cannot really use address sanitizer. Some companies can afford to also compile embedded code to non-embedded platform for testing purposes, but this is not something that anyone could do. And also, when we are using dynamic tools, we are relying on the code coverage. So if we do not execute some part of the code, the dynamic analysis will not find any error in that piece of code. However, if we use static analysis tools, every piece of code can be covered, and also we can do it independently of the architecture we are targeting. And of course, since these two methods are very different, to get the best results, it is great to use both of them because they can complement each other. So let's look at some code snippets. So the one on the left has some row pointers, and basically the row pointer p will point to the local variable x, and the local variable x will go out of the scope, so p will dangle, and then we will dereference a dangling pointer. On the other code snippet, we will have a string view that will similarly refer to a local std_string object, and the std_string object will go out of the scope, and we will have a dangling string view, and if we use a string view, then that is undefined behavior. These two code snippets are very, very similar, and even though they are very similar, most static analysis tools can catch the one on the left, but cannot catch the one on the right. So one of the goals of this work was to find a way to teach static analysis tools to deal with the code on the right part of the slide. And also, if we think about the language rules, they also have some lifetime related concepts in it. So for example, in the second code snippet, when we have an R value, a temporary int object, we cannot take the address of that object to create a pointer to that temporary. So in some cases, the C++ language rules prevents us from committing certain kinds of lifetime related errors. But we can do the same kind of error if we are using user-defined types instead of row types. For example, here, notice the suffix at the test string. We will create a temporary std_string object which will be destroyed by the end of the full expression. So string view will dangle. So optimally, we could be able to define a way so we can teach the compiler that string view actually acts as if it were a pointer, and maybe in the future we could make the compiler not to compile the first piece of code. So probably this is science fiction at this point, but the best outcome of this work would be to change the language rules, so in case string view is properly annotated, the code above will no longer compile. Okay, so Herb Sutter defined an analysis based on some work that was done by others earlier. And this analysis intends to catch many common lifetime related problems. So this is not a verification tool, but more of a bug finding tool. And one of the main ideas of this analysis is to define certain categories for types and categorize each type into one of these four categories. Some of the key observations: we have owners. Owner, for example, stud vector or unique pointer, and owners can never dangle because they are managing their own resources. A vector is always pointing to its own buffer. A unique pointer is always pointing to the object it owns. So we do not really need to check if they are used correctly. Usually we have trouble with pointers that might dangle, that do not own the pointee. And for these pointers, we are essentially doing a points to analysis. We are tracking the possible locations a pointer might point to, and we use this information to try to find certain errors. And the aggregates are the types that we can handle member-wise, and values are everything else. The name of the category might be misleading because there might be types that belong to value category that are actually not value types. So the C++ term value type and the value type category in this analysis are two slightly different things. And the analysis is function local, and right now we have two implementations. One of them was already shipped in Visual Studio, the newest release, and it was developed mainly by Kyle Reed and Neil McIntosh. And the other implementation was done by Matthias Gehr and me, and it is a fork right now, and we are trying to upstream it into mainline Clang. This is the flow-sensitive analysis, and it does not require you to annotate your code. It works without annotations, but in some cases we might need to add some annotations to make some false positive errors disappear. And basically we track points to sets for each pointers, and the points to set can contain null or invalid if the pointer is dangling, or static or local variables, or static in case we are sure that the pointee will live longer than the pointer itself, or we do not want to reason about this pointee. Aggregate members, or no more owned by owners. Okay, let's see. I hope we have internet access. Yes, I should. So this is just a small demo that will hopefully work. Okay, so the point is, on Compiler Explorer there is a version that already implements this analysis, and maybe I'm supposed to increase the font size so you can actually read it. But okay, I think it is better to skip it for now, but you have the link in the slides, so you can look at it later on, or we can come back to it after the talk. But these are basically some small examples showcasing what can this analysis achieve. And let's look at a specific example. So here we have two vectors and an iterator that might point into either one or the other of these vectors. And one of the vectors, we push back one element into one of the vectors, and later on, if we dereference this iterator, we will get a warning because the analysis assumes that the iterator so the iterator might point into one of the vectors that will actually reallocate its buffer, so the iterator will be dangling. And the problem with this approach is that the analysis assumes that any possible path is feasible. So it is possible for the iterator to point into vector 2 and then push back an element into vector 2. But in case cond and cond2 are correlated, and in fact I can never give an input where this specific sequence of events can happen, then this will be a false positive warning. So basically these kinds of errors, these kinds of false positive errors are very frequent in static analysis. We call this the infeasible path problem, and certain analysis needs some kind of discipline for us to write the code from the beginning in a way that it is resilient to those false positives. This way we can write safer code, easier to understand code, but this makes the applicability of this analysis narrower, because we cannot really use this analysis on legacy projects. But do not worry, because by the end of the talk you will see that we actually defined a subset of this analysis that is useful for anyone and that can be used for projects that were not written with this analysis in mind, that have very low false positive rates, virtually zero, and can still find very interesting bugs. Okay, so let's look at some small implementation details. I think the best to show how this analysis works is to walk through an example. So basically, we are working with control flow graphs. Control flow graphs are a specific data structure that is used by the compiler. And the control flow graph consists of basic blocks. A basic block is a sequence of instructions that will be always executed sequentially, and the edges of the control flow graph are the possible branching instructions, so jumps between those basic blocks. So I will show you first how the analysis proceeds within a basic block, so how it proceeds when the instructions are executed sequentially. So let's start with the first sub-expression, that is just the mentioning of a variable x. It's actually an L value. So the point here is that we have some well-defined rules what to do for each kind of sub-expressions, and by following these specific rules, the analysis will derive the right points to set for each of the pointer types. So when we mention a variable and we have an L value, then the rule is to have a points to set for each expression, and for this expression the points to set will be x. So this expression refers to the variable x. And later on, if we see the address of operator, then actually the points to set of this expression is still x. So in fact, the way the unary address of operator works, by default, it's actually a conversion from an L value to an R value. So this will be an R value that have the same points to set. And when we see the initialization, we will store that the points to set of P, which is a pointer, is x, so we know that p is pointing to the variable x. So later on, when we see p, it's an L value, so its points to set is p, and in fact there is an invisible construct that is not visible in the code, but since the Clank compiler will build an AST that reflects the semantics of the code very closely, so there is an implicit cast there that is not visible in the code. We cast the p L value to an R value, and during this L value to R value cast, what we need to do a lookup basically, and we look up in the maps we have where did p point to. So earlier we stored that p points to x, so we can evaluate this the points to set of this expression to be x, and this is how we know that actually q will point to the same variable as x. It is very easy to derive these facts by only looking at the code, but it was a bit harder to actually formulate this formally based on the concepts we have in the AST of the Clank compiler. So basically we are using this representation, we defined these rules, and this was one of the major parts of implementing this analysis. We had to tweak the representation a bit in some places. For example, notice that we do not know where is the end of each expression, because we walk through the sub-expressions, and when we see the end of the full expression, that is where we need to destroy all the temporary variables in our representation. So we needed to do little tweaks with this representation, but otherwise Clang was very useful and very helpful to work with. So let's see what happens when we actually have multiple basic blocks. So in this case we do not only have sequentially executed code, but we have control flow. So we will calculate these points to sets that I showed you earlier for each of the basic blocks, and then we need to do something with the edges. And in case there is a merging point in the control flow graph, for example, after executing the if statement in this code, we need to merge both the then and the else branch. So what will happen? We will take the union of the two sets for each of the pointers. So here we will know that the points to set of p is I in the then branch, and it is null in the else branch. So after this branching instruction, the points to set of p will be either I or null. So this means that p will either point to the local variable I, or it will be a null pointer. So the contents of the set is interpreted as an OR operation. But we do not only need to deal with merging points in the control flow graph, but we also need to deal with forks. So for example here, initially we assume that this argument a might either point to some value, we do not know what value, that is denoted by the dereference of a, or it might be null. So later on, when we have a branch and the branch condition depends on a, we need to be sure that we update the points to set correctly. So to the then branch of this if statement, we will propagate the set that only contains the deref of a, and to the else branch we will only propagate the points to set null. So this way the analysis will know that it is safe to dereference the pointer a within the then branch, but it is unsafe to do so in the else branch. And fortunately, this will also work automatically for the compound checks we have, because the way Clang builds the control flow graph, we will we will see it almost as if we had multiple conditions, multiple nested conditions. So the same mechanisms we used earlier will do the trick. So we will know that it is safe to dereference either A or B in the then branch of A and B, because none of them can be null there. And also, Clang is very helpful to handle no-return functions. So, for example, in case one of the branches will contain a call to a no-return function, then Clang will know that there will be no outgoing edges from that basic block, and we can utilize this during analysis. So we will know that if A were a null pointer, then we wouldn't continue the execution to the next line. So it is safe to dereference A in this example, and we will not give a false positive warning. Unfortunately, this doesn't work all the time. So for example, here, if we hoist the A and B check into a separate variable, we will do the state merging too early, and we will get a false positive warning. The reason why it happens because we need to keep this analysis relatively fast, and we do not want it to consume a lot of memory. So we do not keep track of all the paths. We do each decision locally at the branching points. And the branching point is too early in this example. So it would be possible to solve this issue at the cost of a worse performance, worse runtime performance. And why is this important? It is important because, for example, the way the way the assert macro is implemented in most of the standard libraries, they insert an explicit cast to bool into the condition. So types with explicit conversion operators to bool will work with the assertion macros. And unfortunately, this will force Clang to generate code that is very similar to one before, because the result of the cast operation will be a temporary Boolean variable, and there we will do the state merging. So unfortunately, in this case, we might get surprising false positives with this analysis. This is not something that is impossible to solve. We do plan to add some local path sensitivity that can help us with these cases, but this is something that is very annoying at this point. And this is basically the invisible path problem in action. So because of this invisible path problem, it is not a good choice to use this analysis for every possible project. So to summarize and also give you some more information about this false sensitive analysis, according to our measurements, it has about 10% performance costs on top of compiling, so it is relatively fast, and it has 3 ways of producing false positives, either due to the invisible path problem I mentioned earlier, or due to some type is being miscategorized, which can be solved by adding an annotation, or because of the function modeling. I did not talk about function modeling in depth, but you can check the 2 CPP talks from the agenda slide that will have some details about these problems. Okay, so I promised you that I will show you a subset of this analysis that have no false positives but still finds interesting problems. So the motivation was that we started to look at some of the typical lifetime errors that we would like to catch. In the first example, for example, we will return the memory address of a local variable, and of course the local variable will be destroyed by the time we return from this function. So we will end up having a reference wrapper that is dangling. And we will not get a compiler warning from this, but this lifetime analysis can find this problem. On the next one, when we call the get function, it is even more trickier because that function, that code snippet might work correctly. In case get returns a row pointer, a non-owning row pointer, then this code is safe. Can you tell me when this code is not safe? Do anyone have an idea? Yes, so one possibility would be if get returns a null pointer, that would be the reference of a dangling pointer. But there is another possibility for this to go wrong. What happens if get actually returns a unique pointer? In this case, yes, exactly. Since the unique pointer will be a temporary object, it will be deallocated at the end of the full expression at the semicolon, and we will end up having a reference to deallocated memory, a dangling reference basically. So just by looking at a piece of code, we cannot be always sure whether that piece of code is correct or not. We actually need contextual information. We need to know what the signature of the function get is. And this is one thing that makes it harder to write safe code in C++, and we cannot always remember all the signatures when we write code. But tools, static analysis tools, do remember all the context. So this is why it is a great help to have some tools. And on the third example, we have a lambda that will capture by reference a local parameter, and when we return this lambda, of course this reference will also dangle because the local parameter will be deallocated once we return from the function add. And then later on we have this return expression or return statement, and here again we need to know what are the signatures, because in case name returns a reference to a stud string, then this is perfectly safe and perfectly fine. But in case name returns stud string by value, then we will have a temporary stud string object. We will get back a pointer that is pointing into the buffer of this temporary stud string object, and at the end of the full expression, this stud string object will be released, and we will return a dangling pointer. So this is not something that we would like to do. And in the last example, it is very similar to the one I showed you at the beginning of this talk. So this is about having a temporary stud string and having a string view referring to this temporary stud string. And I wanted to show you one more example. This is from Herb Sutter's keynote. So we have two functions. One is returning a vector by value, and the other is returning a stud optional vector of a vector by value. And in the first case, if we call getVec and get back a temporary stud vector of ints, and we iterate over all the values inside this vector, so the first for loop, for each loop, it is basically perfectly safe. And the reason is that because the way the range-based for loop is defined, it will bind a reference to the return value of the getVec function, and that reference will be alive during the execution of the for loop. So basically, due to lifetime extension rules, when we bind a reference to a temporary object, then the lifetime of that temporary object will be extended to the lifetime of that reference. So due to these lifetime extension rules, the first loop is safe and it will work as intended, no lifetime issues there. However, if we look at the second one will not work as intended. It has a lifetime error because here we will return a stud optional object, which will be the temporary, and we will call the reference operator on this temporary stud optional. And the result of this dereference operator will be an L value, not a temporary object. So the reference within the range-based for loop will bind to this L value, and when a reference binds to an L value, no lifetime extension will happen. So basically, after calling the get opt-vec, the stud optional will be destroyed, and we will use a dangling reference throughout the execution of the loop. And it takes a lot of time to explain what the problem is and what is the difference between these two code snippets. Why is one of them safe while the other is not? Sometimes it is even hard to explain this for very seasoned C++ developers. So this is something that is not easy to grasp and also easy to forget. So this is why I believe we really need tools that can help us catch such problems. And one of the common properties of all the errors I showed you is that none of them has any non-trivial control flow. All of them were just sequence of instructions without any branching or anything like that. So one of the major sources of false positives were the invisible path problem. But if we only look at statement local problems like the ones I showed you earlier, then that path is always feasible. So if we restrict the analysis to be flow insensitive and do not consider all the branches, then we will get something that might not find as many errors as the flow sensitive one, but it will not give us false positives. And this is basically what this new subset of the analysis is about. And it turns out Clang already has some statement local lifetime related analysis. So Clang already warns if we, for example, have a member that will point to have a member pointer that will point to something that will go out of the scope really soon, and it will dangle. So for example, in the first code example, P will point to I, but I will be deallocated as soon as the constructor returned, so P will dangle. And in the next example, we return the address of a local variable. And in the last example, we have an initializer list allocated on the heap. And this will also dangle because the initializer list does not own its memory. So what will happen in this case, the compiler will synthesize a temporary array, and the initializer list will refer to this temporary array, but this temporary array will be destroyed at the end of the full expression, so the initializer list will dangle. So these are existing warnings in Clang, but these are only working for primitive types and one stud type. So the idea was to generalize these warnings so we can find problems like these. So this is what we basically did. We haven't finished generalizing all of them, but we made most of these warnings understand user code. So for example, if we return a reference wrapper instead of a row pointer, in our branch of the Clang compiler, we will also get a warning, not just for the row pointer. So that's the basic idea. And we were curious how efficient this method is. So first we started to evaluate this on LLVM and Clang because this is a code base that we are familiar with. And we did not find any warnings on the head. But it means that we didn't catch any true errors, but it also means we didn't have any false positives. So no false positives, that is good news, but we were curious about whether we can actually find real problems. So what we did, we looked through the history of LLVM and identified 22 lifetime related fixes when developers committed some fix to solve a dangling pointer issue or something like that. So the idea was to look at the past fixes and let's see if these warnings would have prevented the introduction of the original error that was fixed in that specific commit. And it turned out more than half of those problems could actually have been caught by these warnings. So actually it looks like having these simple flow insensitive checks, we can actually prevent half of the lifetime related errors without having any false positives. So this is something that we are really excited about and would like to push into mainline Clang as soon as possible. And it also has very little performance overhead. Okay, so let's look at an example. So some of you might be surprised that the developers of Clang and LLVM, they are developers who are writing a C++ compiler. How is it possible that someone who is writing a C++ compiler will make dumb mistakes using C++? So this might be surprising at first, but let's look at some example why is it possible. So here is a faulty code, and the problem is that we cannot really sure that it is faulty or not because we need the contextual information. So here string ref is the same as string view, and the culprit is that sysroot is actually a stud string, and basically in the ternary operator we need both of the branches, the true branch and the false branch, converted to the same type. So what will happen, since the true branch of the ternary operator has the type stud string, the false branch needs to be converted to stud string. So the empty string literal will be converted into a temporary stud string, and in case the isApps will evaluate to false, then prefix will bind to the temporary stud string. The temporary stud string will be deallocated at the end of the full expression, and we will have a dangling string ref. So basically, in order to identify this problem, we need to know the types of all the variables we have in the expression. We need to know the language rules for the ternary operator. We need to know all the user-defined conversions, because we need to know that a string literal can be converted into a stud string. And we also need to know that a string ref can actually bind to a stud string. So we need to know a lot of things. And when we do a code review, we only see this line as changed. And since sysroot was not changed, I do not see the type of that variable in the online review tool. So unless I open my editor and look at the code in my environment on my desktop machine or laptop or whatever, unless I do that, I do not have the information necessary to find this problem during the reviews. So this is why even the most seasoned developers with a good track record of quality patches to C++ compilers also commit mistakes like this. And the fix was to add another conversion. So in this case, the sysroot will be converted to a string ref. And since both branches will be converted to string ref in this case, the string literal will also be converted to a string ref. And prefix will be a copy of the either one or the other string ref. So no temporary owner will be created, so no dangling in the fixed example. So actually, this is why I believe it is useful to have such a simplistic check in the compiler, because even though it only looks at a very small code snippet and does not consider any of the control flow, it still has all the contextual information that developers can forget about. So this is what makes it useful, and this is why I believe this will be a worthy addition to Clang. And if everything goes well, I really hope that in the next major version of Clang, you can add one simple flag to your compiler invocation and then get useful warnings like this. And the other interesting thing about these warnings is that even though one of my colleagues implemented a similar checker that was path sensitive, that was dealing with all these very complicated control flows, and when she evaluated her check on open source project, she was able to identify bugs in real world code bases, but all the bugs she found Overstatement Local. So even though she implemented all these tricks to make her check path sensitive, all the issues she found were statement local. So it is an interesting question whether we were just unlucky or actually most of the problems in the wild are statement local. Okay, so we plan to upstream everything I showed you, and we plan to, but there is one controversial point, that is the type category inference. So basically, the Bjorn, Herb Sutter, and a lot of people in the standards committee and the static analysis committee wants the type categories to be inferred, so we do not need to touch our code bases, while the Clank community says they want the system to be easier to understand, so they want us to annotate our code, the ownership roles, and according to their argument, basically we only need to annotate very few types, like the standard template library types, a few library types like Boost, because application code rarely introduces its own containers and things like that. So the annotation burden is probably not that high, and it is more precise to have the annotations. So the plan is to not to upstream the type category inference, but instead do a separate tool that helps you annotate your own code in case you have types that you would like to annotate, and you can revise these annotations before accepting them. Okay, so to conclude the talk, we found that Herb's analysis is very useful, it is wonderful, but it is not always applicable to all projects. And type categories are great and useful for to extend existing analysis, and generalized warnings have a very low performance impact because we had ways to counteract all the sources of false positives, and also still since even though they have a low false positive ratio, virtually zero, we were able to find interesting problems using this analysis, and we really hope that it will be upstreamed really soon so you can use it. So that was my talk, and if you have some questions, I will try to answer them.
Thank you for the talk. And my question is, what do we need to do for making this analysis um, as a verification tool,
Mhm.
not bug finding.
I see. So I think it is possible to turn this into a verification tool with relatively low effort. One of the reasons it is not applicable as a verification tool because we do not track arrays that precisely, and or for example each elements of the vectors, because that would make the analysis more costly. And also we do not track the pointers to arbitrary depths. For example, if I have a pointer to a pointer to a pointer, at some point we will stop looking into that. So there are some things that we sacrificed for simplicity, so so the analysis will run faster and easier to implement, and also easier to understand the warnings produced by the analyzer.
Thank you. And another question is about function modeling. Can we use here C++ contracts for better function modeling during the static analysis?
I did not look into that yet too deeply. I believe that it is possible, but one of the information we are really interested in is aliasing, and usually people do not write aliasing related contracts. So I think it is pretty rare that someone would write that, okay, this argument and that argument might alias if that and that happens. So I think most of the contracts do not have the information we need.
Thank you.
Thank you.